And I will share the lecture notes. Let me share my desktop for lecture notes. It's gonna be easier. Okay, what did we do so far? We talked about differential equations. We talked about different modeling examples, right? And also, we talked about how we can solve if we have separable equations and if we have linear first order differential equations. And in this section, we will talk about how we can make sure if the solution exists and if the solution exists, if it is unique or not, okay? So we will focus on two theorems, and according to those two theorems, we can guarantee the regions that the solution exists and it is unique, okay, according to these two theorems. So when considering initial value problem, we need to look at two fundamental questions. Does a solution exist? If a solution exists, is it unique? As I told you, we will focus on two theorems. One of them is for nonlinear, one of them is for linear equations. And these theorems is going to tell us how we can find the regions of existence and uniqueness. Okay, this is what we will be doing today. Let's look at some examples for motivation. Let's determine at least two solutions of this initial value problem. And once you look at this initial value problem, you can see that this is separable because I can write that one as dy dt, and I can collect the y terms in one side, t terms in the other side, just as this one, 2y times 1 over t. So I can write dy over y, 2 dt over t. And you know the deal in separable equations. Once we separate the variables, we need to just take the integral and solve for y. If I take the integral, the left-hand side will be ln y, the right-hand side will be 2 ln of t. Since I want to get rid of these ln's because I want to solve it for y, firstly I can move these two as a power to t, and then I can take the exponential just as I did in here. And what we have just y, e to the ln is going to simplify each other. We have only y on left, and on right we have e to the ln t square, e and ln is gone. We have only t square, and e to the c you can just say some constant k, okay? So as a solution you have y equals kt square. And since it says determine at least two solutions, so for different case, so before that we need to check what is k by looking at this initial value. Let's apply this initial value. When t is 0, y is 0. Exactly, that's true. It is automatically satisfied for any constant k. So whatever the k is, this will be true. Then I can write my solutions as y equals t squared, y is equals 2t squared, 5t squared, 5.3t squared, whatever you take k, this initial value problem is going to be satisfied because when t is 0, y is 0, and it doesn't matter what k is. So you can find infinitely many solutions for this initial value problem. And in general, we don't want that. We want only one solution so that it can work for us, okay? And another one, and this one does not have a solution. Let's look at this. This is a nonlinear, as you can see, because derivative has a power. What did we say for linear differential equations? Derivatives should stay alone, and if there is any coefficient, this coefficient can depend on only t, not y. So this is nonlinear because this one has a power, y derivative square. This is not the second derivative. Be careful about that. This is first derivative squared. That's why this is nonlinear. And let's say we have a solution y of t that solves this differential equation. And once we plug in for that, we can see that this is true only if the derivative and y of t is 0. Okay, and you know that once you take the integral of this one, it will be c, and once you take the integral of that one, you will get something else. So, and two non-negative expressions can have a sum of 0 if both expressions are 0. That's why we are saying that. So there is no solution for this non-linear differential equation. I'm just showing these to you for the motivation. As I told you, you can have infinitely many solutions like the previous example, or you can have no solution for that one. But what you want is a unique solution. And according to these theorems, we can guarantee a unique solution. So when is the first order initial value problem of this form guaranteed to have one and only one solution? And this is the answer. If the function f, which is the right-hand side, y derivative is on the left alone, and the right-hand side there is some function that can depend on t and y, and the derivative of f with respect to y are continuous in some open region containing your initial value, then you can make sure that there is a unique solution in that region. So what is that region? The region that your f and the derivative of f is continuous. So what you need to check? You need to check the continuity region of your f and the continuity region of your derivative. And you need to choose the one that your initial value is in. And this region is the region that you have a unique solution. And out of this region, you cannot say anything. You can have unique, you can have infinitely many no solution, but you cannot guarantee the kind of the solution. Okay? Let's look at this one. dy dt t y to the 1 over 2, and the initial value is given, it's given at 0. And since this is the same as t y to the 1 over 2, I can write as square root of y. And what was the theorem was saying? This f and the derivative of this f with respect to y should be continuous. So the question is right now then, t square root of y is continuous. So t is continuous everywhere, and square root of y is continuous for all t and non-negative y. You know that this is y equals bigger than or equal to 0. If it is negative, you will have complex numbers. So for continuity region, for square functions always, the inside function should be bigger than or equal to 0. So we have the region y is bigger than or equal to 0. So let's take the derivative of y, so this f with respect to y. And this is y to the 1 over 2. And you know the derivative, subtract 1 from the power, and the power goes down, subtract 1 from the power, you have this function, and this function is continuous for all positive y, because y cannot be 0, it is in denominator. So once you get the intersection of these regions, y should be positive, right? Not 0. According to our theorem, for 0 to infinity, there is a unique solution. But look at your initial value. Your initial value is given at 0, but 0 is not in this region. So you cannot guarantee the unique solution for this initial value problem. But you can guarantee if y0 equals 1, yes, there is a unique solution for sure. y0 equals 2, yes. As long as your y is in this region, you can guarantee the unique solution for this initial value problem. And out of this region, no, you cannot say anything. Maybe yes, maybe no. Okay? Do you understand here? Any question? No question? Okay. And here you go. This is the solution of this differential equation. dy ty to the 1 over 2, as you can see. And to be able to take the integral, we need to separate the variables. I moved y to the 1 over 2 here, dt on the right-hand side. I took the integral. The integral of that one is 2 to the y1 over 2. The integral of this one is t squared over 2. You can think this one as y to the negative 1 over 2, and plus 1 over the power is going to give you y to the 1 over 2 as the result of your integral. And right hand side, as I told you, t squared over 2 plus c. And since you are trying to solve for y, if you take the square, once you divide it by 2, this is what you will get as the solution. And once you apply the initial value, which is when t is 0, this is 0, this is 0, c squared, which is c is 0. And so this is your solution. And you can see here that also y equals 0 is your solution when c is 0. So you can see that there is more than one solution. So as the theorem says, no, you cannot guarantee. And as you can see, there are more than one solutions for this initial value problem. But if you use y0 equals 1, you will see that this is the only solution once you get the c. You cannot find another solution that can satisfy for this initial value. Okay? Again, I'm repeating. To make sure that we can have a unique solution, we need to check the regions that f is continuous and the derivative of f with respect to y is continuous. Once we find these regions, as we found it in here, you need to get the intersection of these two, of course, and you need to check your initial value. And you need to choose the one that your initial is in. And in this one, since your initial value is not inside this region, you cannot say anything about a unique solution. And in that one, we showed that there are more than one solution. This is one solution, this is another, and maybe you can find more. Okay? And if the equation is given to you like the linear equation standard form, look at that in here, then you need to check the continuity regions of P and Q functions. And then again, you need to choose the one that your initial is in. Okay? For nonlinear ones, you are looking for the f and the derivative of f with respect to y. And for linear ones, you can look at the pt and qt for the first order differential equations. Look at this example. Determine without solving the problem an interval which the linear initial value problem certain to exist. Okay? Look at that. This is your differential equation, and you need to a standard form by dividing the equation with the coefficient of the derivative, t minus t over 4, t times t minus 4. And once you do that, this is the standard form of your differential equation. And this is your p of t, this is your q of t. And you will be checking where these functions are continuous. For q of t, it is 0, so it's continuous everywhere for any real t. And for that one, t equals 0 and t equals 4 makes your function undefined, so it's not continuous there, but it's continuous everywhere else. That's why your continuity region is negative infinity 0 to 4, 4 to infinity. I took out 0 and 4 from the real numbers. And now check your initial value. Where is 1? Not to 1. You are checking the y. These are the regions for y because. No, we should check t. 2, sorry. Where is the 2 is in? Because we are looking where t is undefined. So, since t is 2, where is 2? No, it's not in here. 2 is in here, yes. So, this initial value problem has a unique solution in the region 0 to 4. You cannot make sure the others, but for 0 to 4, since these functions are continuous, you can guarantee that there is a unique solution in this initial value problem. Okay? So in general, I'm asking one question about that, and the right answers are not so much. That's why I want you to make sure that you understand this. Do you understand it? You can ask me. I can try to explain again. Okay, great. Then let's continue to that one. Look at this one. What is the largest interval in which the initial value problem is sure to have exactly one solution? This is fourth order differential equation. As you can see, we will be talking about these equations too. And this is one of my exam problem, I think, for final or something. So for this, what you need to check is the again, you need to put this one into a standard form by dividing the equation into the largest derivatives coefficient. And that's how we can do that. And for each function, you are checking the continuity regions. For t over t minus pi, other than pi, it's continuous. That's why I'm taking the region from negative infinity to pi, pi to infinity. For second, t ln t. You know that ln t, t should be positive. And t cannot be 1 because ln 1 is 0. That's why it will be 0 to 1, 1 to infinity. And for that one, t cannot be pi, t cannot be 1. That's why I'm taking 1 and pi from the positive t's, because, you know, ln is defined for positive t's. That's why 0 to 1, 1 to infinity, pi to infinity. And for that one, sign is continuous everywhere. And once we look at the denominator, again, t cannot be pi, t cannot be 1, t cannot be negative. And the same with the previous one. And you need to take the, you know, the regions that is true for all of it. And that's why these intervals, we don't have any negativities, 0 to 1, 1 to infinity, infinity to pi. And where is your initial values are defined? T's are defined at 1. So is 1 inside this interval? No, it does not belong to any of these three intervals. So the existence and uniqueness theorem for linear initial value problems does not apply. And there is no interval in which the given initial value problem is sure to have exactly one solution. So we cannot say anything for this initial value problem. But if the initial values are given at 2, you can say that, because 1 to pi, pi is 3.14, you know that. For 2, you can say that, yes, this initial value problem has a unique solution, but not that one. Okay? So if it is given in PQR form, you need to check all the functions that is the coefficient of y terms and the right-hand side. If it is given in F form, just as we did in that one, you need to check F and the derivative of F with respect to y, just as we did in this example. And check the continuity regions, find the intersection of these regions, and check the t of your initial value if it is inside any of the region or not. If it is inside, yes, this has a unique solution. If it is not, you cannot say anything. Yes? Any question? Okay. It is easy. You need to just check functions continuities and put the yes. Any question? Because we will talk about autonomous differential equations if you don't have any question. No questions, I guess. Let me see how many we have. 28. I took attendance. Here you go. So far what did we learn? We learned first order differential equations is in this general form. Y derivative equals f of ty. And first order linear differential equations have this form. Y prime either equals pty or plus pty equals q of t. This is the standard form of linear differential equations. And we learned the first order separable equations if we can separate the t and y variables like that as a multiplication. And now we will talk about the autonomous differential equations. And the autonomous differential equations has this form. Y prime equals h of y, which means that the right-hand side can only depend on y. There is no g. Okay, and we will talk about the dynamics of these autonomous differential equations, equilibrium solutions and all. And let's look at this example. This is a separable equation, dy dt equals ky, and this tells us the law of natural growth or decay. Depends on K. If K is positive, it is growth. If K is negative, we will have decay. And why are we saying that? Let's solve it and check that. And to be able to solve it, I just move the y in here, dt in there, take the integral, ln y. This integral is ln y, right? And this integral is kt, and there is c is coming, indefinite integral. And to be able to solve for y, we took the exponential of each side. I have e to the kt, e to the c is bringing to me another constant a. So my solution is y equals e to the ka. And since the initial is given, when t is 0, y is y0. So when t is 0, e to the 0 is 1, a is y0. So instead of a, I just plugged in y0. And here is the solution of this initial value problem. And as you can see, this is an exponential function. And if k is positive, this exponential function is going to be growing. If k is negative, this exponential function is going to be decaying, going down, right? And this is one example for the autonomous differential equations. And for example, this is another one. This is logistic differential equation. And this is another one. So as long as your right-hand side depends on only y, you can say that you have an autonomous equation. And you can solve these equations with separable equation like that we did in this example. Okay? And let's consider another example. Let's talk about the growth of some amoeba population that doubles every hour. So let's model it. When t is 0, there is one amoeba. When t is 1, after an hour, it's doubled the size. So it was 1, now 2. And when t is 2, it doubled 4. When t is 3, after 3 hours, it becomes 8. And it will go like that. As you can see, when t is 0, it is 1. When t is 1, after 1 hour, 2, after 2 hours, 4, 3 hours, 8 hours, will be 2 to the 8, right? So we are doing the inverse right now problem. We have y of t, which is the population of the amoeba, and it is growing as 2 to the t. And to be able to find the differential equation for that, you can take the derivative of each side with respect to t. And so that you can find the rate of change of the growth of amoeba. So dy dt is dp dt, which is the derivative of 2 to the t. And you know that derivative of 2 to the t is 2 to the t times ln 2. And since ln 2 to the t is y, instead of 2 to the t, I can write y. So my amoeba growth differential equation is dy dt ln 2 times y. It is the differential equation of population growth. And since k, which is ln 2, is positive, it's a growth. So when t is increasing, the population of the amoeba is increasing, right? So this is what you can do also. Once you have the solution, you can have the differential equation, the rate of change, by looking at this solution. Okay. And why are we doing that? Because we can do some geometrical analysis by looking at the equilibrium solutions and what is that, direction fields of these differential equations. Here you go. You know what is equilibrium solution. We talked about in the first class. We said that if y prime equals 0, we can find the equilibrium solution. And these solutions is telling us how our solution is going to behave if we start with different initial values, right? And we have a phase line. It gives a quick description of the behavior of the solution. And as you can see, these are the phase lines. I plotted a couple of them. And why did I plot it separately? Because we will call them in different names. For example, if a solution approaches to the equilibrium solution as t is going to infinity, then this equilibrium solution is asymptotically stable. So this is what we call a stable equilibrium. And if the solutions are diverging from the equilibrium, we have unstable solution. And if the solution is approaching from one side and diverging from other side, this is diverging, this is approaching, as you can see, or the vice versa. It can approach from here, it can diverge from here. And these kind of solutions, we have semi-stable solutions. Okay. So if both way it is approaching stable, if both way if it is diverging unstable, if one is approaching, other one is diverging, we have semi-stable solution. Okay. And now how we are finding that? We will do a couple examples. Look at this logistic equation. dy dt equals, this depends on only y, so it's an autonomous equation, and I can easily check the dynamics of these equations. And to be able to do that, we need to find the equilibrium solution as a first step. So once we make this one equal to 0 and solve for y equals 0 and y equals 3 over 2, we have two equilibrium solutions. And as the B part, let's sketch a phase line. So phase line means that we need to check the regions other than equilibrium solutions. So since my 0 is equilibrium, we have minus infinity to 0, 0 to 3 over 2, 3 over 2 to infinity. So I can divide the region into three different ones. And for minus infinity to 0, check the y's. So let's take negative 1. If y is negative 1, this will be negative, and this will be positive. Positive plus negative, it will be negative. Sign will be negative. So I'm just plugged in one value, choose just one value from this interval, plugged on the right hand side, and check the sign. I chose negative 1, negative 1, this is positive 1, this will be 3 plus 2, 5, so negative 5, it will be negative. And if it is negative, which means that it is decreasing, okay? All the, slopes in this region is gonna be decreasing because it's all negative. And from 0 to 3 over 2, let's choose 1. If it is 1, this is positive, this is positive. So positive times positive, positive. Then it will be all increasing. And for 3 over 2 to infinity, choose 2. So this is positive, this is negative, negative times positive, negative. So it's all decreasing. And as you can see here, we have 0 and 3 over 2 as an equilibrium. And for 0, both is approaching to 0. So if I want to classify the solutions, y0 will be what? In here, look at that. For negative infinity to 0, you can easily understand by sketching the solution curves. Look at that. I put 0 here, I put 3 over 2 there. And for negative infinity to 0, what did we say? It is decreasing. It is decreasing. For 0 to 3 over 2, it is increasing. And for 3 over 2 to infinity, it is decreasing. So once you look at it here, 3 over 2 is a stable equilibrium because it is approaching, the solutions are approaching to 3 over 2 from both ways. So 3 over 2 is stable. And once you look at the 0 equilibrium, all solutions are diverging from 0. That's why it is unstable equilibrium. Is it clear? And in that one also you can put it in there and you can look at that. 0 is here, negative infinity to 0, it is decreasing, so it's going to the negative part. 0 to 3 over 2, it is going to the positive part. 3 over 2 to infinity, since it is decreasing, it is showing the negative way, the arrows. And once you look at 3 over 2, both is approaching, so stable. Once you look at the 0, both is diverging, so it is unstable. Any question? No? Okay. Let's look at this example. Okay, great. Look at the equation. Find the equilibrium solutions and sketch the phase portrait of the differential equation. So you know how to find the equilibrium solution. Make the right-hand side equals to 0, which is y equals 0, y equals plus or minus 2. So y0, y2, y minus 2. You can put it in like that to 0, 2, minus 2. And now you need to divide the region into 4 pieces. From negative infinity to -2, -2 to 0, 0 to 2, 2 to infinity, because you have 3 equilibriums, 0, -2, 2. And now from the region minus negative infinity to the -2, choose 1, -3, plugged in on right hand side. So this is positive, this is negative, it will be negative, which means that in this region, the solution curves will be decreasing. So negative infinity, -2, the solution curves are, decreasing, as you can see. Negative infinity 0, choose -1. So this is positive, this is positive, it will be positive. Then the solutions curve are increasing. For 0 to 2, choose 1. So this is positive, this is positive, it is positive, then it is increasing. For 2 to infinity, choose 3. This is negative, this is positive, multiply negative. So it is decreasing. And look at this in here. For -2, both solutions are diverging, so it is unstable. For 0, it is approaching, it is diverging. So one way approaching, one way diverging. So it is semi-stable. And for 2, it is approaching from both ways, so it is stable. As you can see, you have 3 different equilibrium solutions, and all 3 are in different way in behavior. Okay? Is it clear? Okay, great. Now I want to, let me check that one. I asked one question before about this. Great. If you have any question, you can ask to me. And in general, you will have one question about it, and I want to show that to you from last year. What did I ask? So that you can have an idea. Where is that? Here you go. This was one of the exam questions from last year. Consider this differential equation. Find the equilibrium solutions. Draw the phase line. Classify each equilibrium. And if the initial condition is applied, what is the limit as t is going to infinity? Okay. And as the first part, look at the differential equation. The right-hand side is only depending on y, so it's an autonomous equation. I can easily check the dynamics of it. So the first step for that, we need to find the equilibrium solutions. Make this one equals to 0. What you have y times 3 minus, y times y minus 3. You can factor this one with y. You have y equals 0, y equals 3. And for that one, if you take the logarithm ln of each side, you have y equals logarithm 2. You have 3 equilibrium solutions. You can see that, right? Everyone understand this part? I think you did. Oops. Let me check. Great. And what else? Here you go. Draw the phase line. So since you have 3 equilibrium values, you need to divide the region from negative infinity to 0. Logarithm 2 is 0.6. So 0 to logarithm 2, logarithm 2 to 3, 3 to infinity, right? You have this region, that region, that region, and that region. And for this region, you are choosing one value. You can choose -1 for there. Plug the -1. Look at the sign. You will see that it is it's positive. So it is going to the positive side. For 0 to logarithm 2, you can choose 0.1 or something. And you will see that this is gonna be negative. So it is going to the arrow is showing to the negative part of the axis. And for logarithm 2 to 3, you can get just 1 plugged in. look at that the sign, it will be positive. So the arrow is showing the right hand side. For 3 to infinity, get 4 plugged in. You will see that it's negative. So the arrow is showing to left. And for there, you can see it easily, right? So 0 is what? Both is approaching. 0 is stable. And logarithm 2, both is diverging from logarithm 2. So this is unstable. And for 3, again, both is approaching to 3. Then it is also stable. So 0 and 3 is stable. Logarithm 2 is unstable equilibrium. And look at this C part, please. If the initial condition y0 equals 1, what is the limit when t is going to infinity? So when y is 1, look at the 1. If your initial value is 1, 1 is where? It is somewhere here, right? Because logarithm 2 is 0.69, so it is somewhere here. And if your initial is somewhere here, follow the arrow. Arrow is approaching to the right, and it will reach to the first equilibrium, which is 3. Then the limit will be 3. As you can see, our phase line describes what happens to the function y for various values of y. Looking at the phase line, we know that 1 belongs to between logarithm 2 and 3, and hence the solution will tend toward the equilibrium solution 3 in the limit, and it will stay in 3 in the long run. Is it clear? So today we talked about two theorems that can tell us the part B. Part B, of course. Part B here, classifying that one. So it is the same as drawing. Let me, you can see that, right? I'm still sharing. Yeah, I'm still sharing. Let me try to put it in that one. The one that I was putting. I will get the graph tablet. Hopefully this week it will arrive to me. And at that time it will be easier for all of us. So we have how many? We have 3 equilibrium points. So I can divide my region into according to the 3. And from smaller to the big, smallest to the biggest. This one is what? 0. Let's say that y equals 0. Oops. This one, sorry, here you go. Y equals 0. And this one is y equals logarithm 2. Just to make it clear for you, I'll plug in log 2, or you can write ln 2. Both is okay. Okay. And this one is the biggest one, 3. Right? So from negative infinity to 0, you are choosing one value. So choose negative 1. Plugged in here. Negative 1 square is positive. 1. 1 minus 3 times negative 1. This is going to be negative, 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 positive. So this will give me a positive something. If I get any number less than 0, this will be positive, right? And if I get, what about here? 2 to the e to the negative 1. Is it going to be positive or negative? It will be all exponential is increasing, right? Like that. And e to the negative is going to be always less than 2 in that one. So negative it will be. And 2 negative, negative, it will be positive, positive times positive, so it will be positive. That's why this is going to be always increasing. And just as we were doing before, you can add some arrows in there. So these are going to be all increasing in that part. And for 0 to logarithm 2, take 0.1 plugged in and check the sign of the right hand side. And you will see that this will be negative. That's why you need to have the arrows that is going to be decreasing in that part. Okay? And by looking all the regions, just take one value, put it inside your right hand side, check the sign. You can use calculator for that, or you can guess. Is it clear? And you can have all these regions and how the solutions is gonna behave. And then since it is approaching to 0, this is gonna be stable. Remember that. And these are gonna be logarithm 2. You can see here one is decreasing, one is both is diverging from logarithm 2. So this is unstable. And the same way y3 is stable because both is approaching. Okay, just choose one value in those regions, put it on the right hand side, look at the sign. If it is positive, put the arrows increasing. If it is negative, put the arrows decreasing. Or if it is positive, put the arrow showing to the right. If it is negative, put the arrow showing to the left. And then check that, how the solutions are behaving. Is it approaching? Is it diverging? Okay. Yeah, it is a little bit hard without, writing. But you can ask to me anytime. And I will not go further from here. We will talk about exact equations and we will be talking about second orders next week. And also some numerical solutions. We will be finishing the second order next week, hopefully. After that, we will be talking about higher order differential equations and Laplace. And then, do you have a question? I already assigned your first homework. And after Thursday, I will assign your second one. And your exams will be also on Pearson. Make sure that you get used to the system. And in the meantime, if you will have any question, you can ask to me. If not, we can finalize the class today in here. Okay, Ceren. Okay, yeah, you can mail to me. Let me stop recording.